All right, we're about to go through the August 2023 exam step by step. Are you ready? All right, first let's look at the conversion chart. So for the scale score, that's what's going to be reported. For a 65, you need 51. But to get mastery, which is an 85, you need 75 points. Well, that's more than 20 points. Why? Look at this. I have two 66s. I have two 73s. Two 77s. You see that? It makes it harder to get up there, okay? So in between 65 and 100, the scale gets harder, all right? Also, look at this sort of rudeness here. There's two 64s, two 63s, two 61s. So it is really hard to get from 60 to 65 because that is not just 5 points, it's more than that, okay? So as a general rule, I say you should always aim for at least 35 multiple choice questions correct, but aiming for 40 is better. And then you will get some points then from the short answer questions. So aiming for multiple choice between 35 and 40 questions correct, so you get enough on the other parts in order to pass or get mastery, okay? All right, we're going to start looking at the August 2023 exam for chemistry. Okay, so you can see our date here. The materials that we have available are the exam booklet. We also have the answer booklet, and then you will have a copy of the reference tables. Okay, so we're going to go through this exam question by question. Remember that you have to have a calculator, not a graphing calculator. And then these are the 2011 reference tables, which was the last time they were updated. Okay. In Part A, we have 30 multiple choice questions. These are going to be the relatively easier multiple choice questions, meaning typically we're not solving problems. Typically it's not very multi-step problems, pretty straightforward content. Okay. Question 1. Which proposal in the development of the modern model of the atom was made before the others? Okay, so let's think about the model of the atom over time. So it started out just as this solid sphere, like Dalton thought. Then we had Thomson's model, which had negative electrons in a positively charged ball. Okay. Then we had Rutherford, where we had a nucleus, and then we had electrons in orbits. And then we had the Bohr model, where we have a nucleus and we have electrons in energy levels. And then finally the modern model, or the electron cloud model, where we have electrons in orbitals. Okay, so which model was made before the others? So what really came first? This. Atoms were hard, indivisible spheres. Okay. According to the wave mechanical model, in the ground state, the 10 electrons of a neon atom would be located. Okay, so where are electrons located? Kind of, we just talked about it. In the wave mechanical model, which is the electron cloud model, which is the modern model, where are the electrons? They are always in orbitals. Okay. Number 3, which statement describes two different isotopes of carbon? Well, isotopes by definition have the same number of protons, a different number of neutrons, which means they have the same atomic number. So yes, they have the same atomic number. No, they do not have a different atomic number. And no, they do not have a different atomic number. So they have the same number of protons, but a different number of neutrons. So same atomic number, same number of protons, different mass number, or different number of neutrons. Okay. Number 4, an element that is a very reactive metal could have an atomic number of. All right, so let's go to the periodic table. All right. And we have 9, 2, 19, and 79. Okay, so 9, atomic number 9. What else do we have? 2, 19, and 79. 2, 19, and 79. So a very reactive metal. Well, first of all, this is not a metal, that's a noble gas. This is not a metal, that's a halogen or a nonmetal. Now we have gold and potassium left that are metals. Group 1, though, has the most reactive metals. Group 2 would be the next reactive. So that means it would have to be atomic number 19. Okay. Number 5, which element is listed with the number of protons? What is the number of protons? Protons is the atomic number. So let's check them. Does nitrogen have 14? No, nitrogen has 7. Silicon, does silicon have 14? Oh, yes it does. Let's just check. Oxygen and phosphorus. So oxygen does not have 16 and phosphorus does not have 16. So we were right, silicone. All right. Number 6, what is the overall charge on the nucleus of a fluorine atom? Well, here's fluorine. What do we know about fluorine? The nucleus contains protons and neutrons. Well, neutrons don't have a charge, so they don't contribute. So only the protons contribute to the charge of the nucleus. So that means it would have to be positive 9 because its atomic number is 9, so it has 9 protons. Number 7. As the elements with atomic numbers 11 through 17 are considered in order of increasing atomic number, the classification of the elements changes from. So I'm looking for atomic numbers 11 through 17. So 11 through 17. So am I going across a period, right? But I don't get to noble gases. I just go from sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. As I go that way, I go from what? Well, it starts with metals, so those two are wrong. And metalloids are in the middle because they kind of have properties of metals and kind of have properties of nonmetals. So it's metal, 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 metalloid, nonmetal, nonmetal, nonmetal. Okay. At STP, which property could be used to differentiate 1 mole samples of Cl2 gas and Kr gas? All right, well, phase. Phase is state of matter. Well, they're both gases. Okay, pressure. It says they're at STP, so that's standard pressure, so that's not different. Well, it's either chemical reactivity or temperature. Well, again, STP is standard temperature and pressure. So the only thing that would be different, and again, that ties to the periodic table, Kr is a noble gas, and Cl is a very reactive nonmetal in a halogen. Okay. Number 9. 2 gaseous forms of oxygen are diatomic oxygen and ozone. These 2 forms of oxygen have. So first of all, you'll notice that one is O2 and one is O3. So first of all, do they have the same structure or the same properties or different structure or different properties? So you can see I'm comparing structure and properties. Okay, well, think about it. Do oxygen, diatomic oxygen, and ozone have the same properties? No, absolutely not. They have completely different properties. So that eliminates same properties here, same properties here. Now, think about it. If they have different properties, would they have the same structure or would they have a different structure? Yeah, they would have different structure and different properties. So this is a vocabulary word called allotropes. Okay, allotropes are the same element, but they have different structures, and as a result, they have different properties. Okay. All right, number 10. A compound consists of 2 or more different elements that are, okay, well, so a compound, for example, is CO2, right? Or NaCl. How are they combined? Well, you should know that they are chemically combined. That is true. They are not physically combined. Those are mixtures. So if they're chemically combined, are they chemically combined in a fixed proportion? Like, is it always CO2 when it's carbon dioxide? And is it always NaCl when it's sodium chloride? Yes, absolutely. In a proportion that can vary, talks about a mixture. Okay. Number 11, compared to the chemical and physical properties of the compound CO, the compound CO2 has, well, they're different compounds, right? That means they have different properties, not just different chemical properties, but different physical properties as well, right? Number 12, which phrase describes the molecular polarity of and the charge distribution in an HCl molecule? Okay, so let's go to the periodic table and table S for a moment. All right, so looking at the electronegativity, you can see the electronegativity of H is 2.2. The electronegativity of chlorine is 3.2. So this would be H connected to Cl. This has 2.2 as the electronegativity. This is 3.2. Okay, so when I subtract those numbers, I get 1.0. That makes it polar. Okay, so I know nonpolar is wrong. If it's polar, then it has to be asymmetrical charge distribution. The electrons are going to be pulled more strongly toward chlorine, which has the greater electronegativity. Okay. Number 13. Which atom forms an ion with a radius larger than the atomic radius? Okay, let's go to the periodic table for this one. Okay, so here we are. Which elements am I looking for? I am looking for calcium, oxygen. All right, so calcium, oxygen. What else? Lead and tin. So lead and tin. So tin and lead. Okay. Which one forms an ion with a radius larger than the atomic radius? Okay, well, if we look, calcium has an oxidation state of +2. Tin can either be +2 or +4. Lead can either be +2 or +4. And look at oxygen, -2. What does that mean? That means oxygen gains electrons when it becomes an ion. So the ion will have a larger radius when we are talking about oxygen. All right, number 14. Which sample can be classified as a substance? Well, what is a substance? A substance is either an element or a compound. Okay. So if we're looking at those choices, which one is an element or a compound? It is argon. It is here on the periodic table, a noble gas right here. Number 15, a 1.0 gram sample of NaCl solid is dissolved in 100 grams of water at 25 degrees Celsius, and another 1.0 gram sample of NaCl is dissolved in 50 grams of water. Which property of the two resulting mixtures will be different? Well, they contain the same components, so the color will not be different. Will the particle size be different? No. Will the polarity of the components? No, it's literally the same stuff. So the only thing that will be different is the proportion by mass. The one that I add 1 gram in 100 grams of water will have more NaCl, less NaCl than the one that is dissolved in 50 grams of water. Like the 100 grams of water, it's more dilute. It would have a lower percent by mass. Okay. And number 16, based on table G. Okay, what should we do? Let's go to table G. Okay, so here is table G. what do I need? Which compound has the greatest solubility in 100 grams of water? Love to see 100 grams of water. I don't have to do any tricks. At 10 degrees Celsius. So what I'm going to be doing is going up from 10 degrees Celsius, and I want to find the substance that crosses this 10 degrees Celsius line the highest, because that will have the greatest solubility. So my options are NH4Cl, which is here, right? What else? HCl, NaCl. So HCl, that's right here. NaCl, that's right here. And NH4Cl. And NH4Cl, we did. NH4Cl, HCl, NaCl, KCl. How did I miss KCl? Okay, and KCl is right here. So which one has the greatest solubility? Well, the one that crossed way up here, that is HCl, right? Number 17, according to the kinetic molecular theory, ideal gas particles. Well, they are separated by little distances. No, they're separated by large distances. They do not transfer energy when they collide. No, they in fact transfer all of their energy in an elastic collision. Have attractive forces between them? No, they have no attractive forces. So this must be it. They move in random. Yes. Constant. Yes. Straight line motion. Absolutely. Those are ideal gas particles. A reaction is most likely to occur when the reacting particles collide with proper orientation and proper energy. Remember that. They gotta, bam, hit hard enough. Okay? Number 19, a sample of SO2 gas and a sample of NO2 gas contain the same number of molecules when they have the same, they have to have the same temperature. And if I remember they have to be at the same temperature. Okay, so I know this one is wrong, right? So what else is true? Do they have to have the same mass? No, because their particles can be different. So that means they have to have the same pressure, the same volume, and the same temperature. That's Avogadro's law. Number 20. Which term identifies the strong intermolecular forces found in a sample of liquid water? Yeah, that's hydrogen bonding. Okay. Which mathematical expression represents the heat of reaction for a chemical change? Well, we do potential energy of the products minus potential energy of the reactants. Okay, there we go. 22. Catalysts can increase the rate of a chemical reaction by providing. So real quick, here is a potential energy diagram. All right, let's change the color. If we added a catalyst, we would start the same, we would end the same, but we would have a different pathway. So alternate pathway, yes, not same, not same. And the activation energy for the catalyst is there, but the activation energy for the original reaction is there. So it's an alternate pathway with a lower activation energy. Number 23, which term represents the disorder of a system? Straight up definition, entropy. Entropy is disorder, okay? Number 24, which element must be present in all organic compounds? Now, you could get a little bit of a hint from the reference tables. If you go back to table P, organic, and look what it says. Okay, carbon. Now, in reality, it's almost always carbon bonded to hydrogen, but what must be present is carbon. Based on table R. Okay, so I'm going to, first of all, get to table R. Which functional group allows a compound to be classified as an organic acid? So find organic acid. The title, see, functional group, it should look like that. So I'm going to go back and find the one that matches exactly. Okay. And almost done with part A. So 26. In a voltaic cell, oxidation occurs. All right, so here's a phrase. Leo says grr. Right? Now you can also remember oil rig. Okay, that helps you with oxidation and reduction, but it doesn't help you yet with where it happens. This says losing electrons, oxidation, gain of electrons is reduction, and this says oxidation is loss and reduction is gain. But that doesn't tell me where it happens, so you have to remember another phrase, which is an-ox and red hat. Okay, an-ox, anode, oxidation, red hat, reduction, cathode. So oxidation, that's the anode. All right, number 27. Which positive ion must be present in an aqueous solution of an areneous acid? Well, it's hydrogen, but I don't see hydrogen, right? Okay, so what I have to remember is hydrogen is very clingy and will find a water molecule and attach itself to the water molecule. And so we're looking for hydronium. So it could have been H+, but H+ isn't an option, so it's hydronium. Number 28, a change that converts an atom of one element to another element. So a change into a new element, transmutation. Okay. Which radiation has the least ionizing power and the greatest penetrating power? So I'm going to look at a reference table for this one. I'm going to go to table O, right? Now, if it has, let's go back and look, if it has the greatest penetrating power, so that means it can get through a whole lot of stuff. So if you look at alpha particles, they have a mass of 4. That means something as thin as a sheet of paper, bonk, can't get through. Okay, so I don't want something with a big mass. So that's going to eliminate alpha particle. It's going to eliminate proton. Okay, it's going to eliminate neutron. Those have the biggest numbers on the top. So they will get through the least. Okay, now what will also stop it is if it has a charge. Okay, and so I'm going to eliminate beta particle. I'm going to eliminate positron. So the one that is able to get through the most things, so paper and then foil, and then even some of the thickness of a big slab of concrete is going to be gamma radiation. Now, because it has the greatest penetrating power, it has the least ability to bonk into something and make it lose an electron. So it does have the greatest penetrating power, but the least ionizing power. Okay, now which nuclear emission is listed with its notation? You literally use table O and match them up. Which one is correct? Well, you will see that it is a beta particle that is matched correctly. And we finished part A. All right, now we are on to part B1. These are the harder multiple choice questions, but there's only 20. So number 31, diagram 1 represents an atom of hydrogen showing the nucleus and the electron in the first shell. Okay, what is represented by diagram 2? Well, you can see we still have the nucleus, that's the same. There are 3 energy levels still drawn in both, but you can see the electron is now here. It was here and boop, it went up. Okay, so did the number of electrons change? No, so it cannot be an ion because an ion requires either gaining or losing electrons. So what is diagram 2? Well, the electron has moved up to a higher energy level. And what do we call that? Atom in the excited state, right? Okay. Number 32, the table below gives the atomic mass and the abundance of 2 naturally occurring isotopes of copper. Which numerical setup can be used to calculate the atomic mass of copper? So what do we need to do? We need to take the atomic mass in atomic mass units and multiply it by the natural abundance. So this times this times this, okay? So first of all, this I can see is paired with the wrong thing. Okay, that looks paired correctly. This one is paired with the wrong one. Okay, so you should easily be able to match up to two possible correct answers. Now, here's the thing. This is in percent. And in reality, we can't do math with percent. I could say it's 62.93 times 69.15%, right? But neither of these answers say that. So that means I have to change the percent into a decimal. How do you do that? You divide it by 100. Okay, so the correct answer will be here, where we have the correct numbers matched up, and this is the percent divided by 100. And you do this one times this one times this one, and then you would add up those answers to get the atomic mass. Number 33, which subatomic particles were discovered as a result of experiments with cathode ray tubes? That was electrons with J.J. Thomson. So here's the cathode ray tube with a beam of particles going through it. When it was placed within a magnetic field or an electrical field, this beam of particles was attracted toward the positive side, indicating it had a negative charge. Okay. Number 34, which change in electron location in an atom of calcium is accompanied by the greatest amount of energy emitted? Okay, so that means given off. Let's just look. So we have shells 4. Okay, we don't ask anything about 3, but let's put it in the diagram. 2, and here's shell 1. Okay, so here's the nucleus in the center. So imagine those are complete circles. So let's switch the color. So our first one goes from shell 1 to shell 2. Okay, that's this one. All right, our next one goes from shell 2 to 1. Okay, let's switch our color again. And we're going to go from 1 to 4. Okay. And then our last one, let's go here. We are going to go from 4 to 1. Okay. So which change is accompanied by the greatest amount of energy emitted? Well, if energy is emitted, it goes from a higher to a lower energy level. So that means the ones that went up, so this one, right, and this one are wrong. So which one would emit more energy? Yeah, when it drops more shells, okay? Number 35. As the atomic number increases in group 2 from Be to Ba, the first ionization energy. So you can see that it's asking first about first ionization energy, but also atomic radius. Okay, so this is table S, right? So here it's saying from Be to Ba down this group. So let's look at just the first three, Be, Mg, Ca. Okay, so let's find them here. Be, Mg, Ca, right? So here's Mg, here's Be, right? And here's Ca. So those are the first three. You can definitely see a pattern. So what is happening to first ionization energy? What is it doing? Well, okay, it's decreasing. So that means the first ionization energy is not increasing. I'm already at a 50-50. So what is happening to atomic radius? That's over here. So here, then here, then here. So what's happening to atomic radius? It is increasing, right? So use the reference table, right? All right. All right, number 36. Given this equation, what is the mass of Mg3N2? So what is the mass of that? That is produced when 14.58 grams of magnesium right, is completely reacted with 5.60 grams of nitrogen. So here's my two sides of the equation. Law of conservation of mass says that the amount of mass on both sides must be equal. Mass is not lost, mass is not gained, mass is not created, mass is not destroyed. So let's think logically. First of all, I know this can't be it and this can't be it. I can't add 14.58 and get less than 14.58, right? And there's no way I'm going to get 49 when I add 14.58 and 5.60. But you can also just do it in a calculator and find out that 20.18 is the correct answer. Number 37. Which Lewis electron dot diagram represents a model of H2S? Well, first I'm going to find two wrong answers and give myself a 50-50. Okay. First of all, do you see this? How we have unpaired electrons? Yeah, no. Lewis dot structures must pair up all electrons. Okay. Now let's look at what's left. Okay. Now you might not be sure which one is correct. So let's get some help from the reference table. So let's go to the periodic table and see hydrogen has 1 valence electron and sulfur has 6. Okay, so sulfur looks like this: 1, 2, 3, 4, 5, 6. And then I have 2 hydrogens. Each of them look like this, right, with 1 valence electron. So what will happen is this electron right here will pair up here and we'll get a hydrogen. And then this one will come over here, and now everything is paired up. So what does that look like? Yeah, that looks very similar. Although it's on this side, that doesn't matter. This is the same structure as this. It's just rotated. Okay. Number 38. What is the vapor pressure of water at 90.0 degrees Celsius? Okay, that's a reference table question. What reference table? I don't know, the one that's titled vapor pressure. So at 90 degrees Celsius, and I want to know for water. So find 90, 75, 80, 85. Here's 90. And go up to where it touches. I want to know where it touches water, right? Right here. Okay, that's water's line. And go over. Okay, so we're roughly around here. This goes by 10, 60, 70. So it's between 60 and 70. Do I have an answer that is between them? I sure do, right there. Number 39. A sample is composed of 2 different substances that can be separated by using filter paper. This sample is classified as, so what is it? Well, first of all, if it can be separated physically using something really simple like filter paper, then I know it's a mixture. So those are wrong, right? And what kind of mixture would it be allowed to separate with filter paper? Well, I'd have to have solid pieces stuck on the filter paper, right? And a liquid that went through the filtered paper. So it would have to be a heterogeneous mixture. It was not evenly mixed, it was separated. Number 40, which solutions react to produce an insoluble compound? Now they're saying solutions because every single one is AQ, and AQ means dissolved in water. So KCl is aqueous is a solution, and LiCl aqueous is a solution. So it's a mix of solutions, okay? Which one will react to produce an insoluble compound? Well, we need a reference table. What we need is table F. So this is solubility guidelines. You can see here we have soluble and insoluble. So what I want you to notice here is let's look at the metals. Okay, so K and Li. Well, Li right here is group 1, always soluble. Now what it doesn't tell you is it just says etc. That's kind of a pet peeve of mine. I hate that it does that, because what you need to remember is on the periodic table, K is also there. LiNaK. Now we also have rubidium, cesium, and francium. Those are just used less often. I wish it was LiNaK, etc. Unfortunately, that's not the case. So when I go back to table F, one of the things I'm going to think about is that this includes K+. So that means K will always be soluble and Li will always be soluble. So that's a wrong answer. So I know Li will always be soluble, right? Na, well, that also right here. So Na will always be soluble. Again, not possible. Okay? Na, again, always soluble. K, always soluble. All right. Now, so here's my outlier, Ag. Right? Now, currently, Ag is combined with ClO3 in both of these cases. Now, in this reaction, it would switch places. So I would end up with AgCl because the Ag and the Na swap. And I would end up with AgNO3. So one of those is going to be insoluble. So let's find out. Well, here is NO3. Look at that. No exceptions, always soluble. So this one right here is soluble, which means it must be AgCl. Let's see why. Okay, well, here's Cl, and Cl is always soluble, but when it's combined with Ag plus, as an example, it breaks its rule. It flips to the other side and it becomes insoluble. So the correct answer is going to be number 3. All right, what is the amount of heat energy absorbed when 40.0 grams of water is heated from 10.0 degrees Celsius to 30.0 degrees Celsius? Okay, we obviously need a formula, right? So we're going to do a calculation. So there are 3 heat formulas. Only one involves a change in temperature. So I need Q equals MC delta T. All right, so Q equals M is 40. I could write 40.0, but why? C, where do I find C? Literally on the opposite end of the periodic table. Specific heat capacity for water right there. So that's 4.18. Now, delta T is final minus initial. So 30 minus 10. All right, now we need to do this calculation. Okay, so we need to do 40 times 4.18 times 30 minus 10, which is 20. Okay, so 40 times 4.18 times 30 minus 10, which is 20. Okay, what is that going to give me? 40 times 4.18 times 20. I get this. 3,344 joules. Okay, so which answer is that closest to? Well, it's this one, because this is the same as moving that decimal point 3 places. So it is this number rounded. Okay. And number 42, given the formula representing a compound, what is a chemical name of this compound? Okay, so let's try and find the longest branch of carbons I could have. So this, counting this way, would be 5. Counting this way would be 3. Counting this way would be 4. Counting this way would be 4. And counting like this would be 4. So the longest one I could have is a 5, right? So what is the prefix for 5? Well, that's a reference table question. I go here to reference table P, which lists the prefixes for carbon chains, and 5 is pent. So the chain name comes at the end. So it's not butane, it's going to be pentane. So now it's one of those options. So now which carbons were not part of this chain? Well, this one and this one. Okay, now are those carbons connected to each other? No, they're not. So what is the prefix for one carbon? Meth. So this is a meth, and this is a meth. Those 2 carbons are not connected to each other, So it's going to be this one, number 3. All right, we are almost done with B1. We're on number 43. So here's a cooling curve. During which intervals is the potential energy decreasing while the average kinetic energy remains constant? Well, remember, average kinetic energy is related to temperature. So where temperature is constant is where that line is horizontal. So that's going to be BC and DE. So there we go. Okay. Number 44, which formula represents a hydrocarbon? Hydro meaning it contains hydrogen, carbon meaning it contains carbon. Literally just those two elements, hydrocarbon. Which type of organic reaction produces carbon dioxide and water? Okay, so let me go through the organic reactions. So the acronym that I remember is PS faces. Okay, now I'm going to type. What does the P stand for? Right, I'm going to type the whole name. Polymerization. So that's making a polymer, a big molecule, from a bunch of monomers. Okay, what is this S? Saponification. That is making soap. Okay, and you need a strong base. So think an OH for that. F stands for fermentation. So that is making alcohol and carbon dioxide. So those are the products. Okay. Then we have addition, and addition is adding 2 atoms, okay, after breaking usually a double bond, okay? And often we add a halogen or hydrogen, okay? C is combustion. Combustion is burning, okay? The products are carbon dioxide and water, all right? And then we have E, esterification. So that is making an ester, okay? And then lastly, substitution. Okay, substitution is swapping out 1 atom. And again, it's usually a halogen that is the one that's swapped. Okay, a halogen for a hydrogen. So let's go back to the question. Which type of organic reaction produces carbon dioxide and water? Yep, it's combustion. Okay. All right, 46. Which half reaction equation represents the oxidation of lithium? Okay, so what I'm going to do is just show you real quick. I'm going to draw a number line, but just like this, really short. Okay, it continues on, obviously. So now you should remember these phrases. Leo says grr, right? So losing electrons is oxidation. Gaining electrons is reduction. So when I go this way, right? Okay. Am I losing or am I gaining electrons? Well, I'm losing. The number is getting more positive. It's getting bigger. So losing an electron is losing a minus, which means you get positive. And so going this way is reduction, right? So now I'm focusing on oxidation for this question. The important thing here is this arrow. So that means when we lose electrons, they are on this side, the product side of the equation. So that means this and this are showing reduction. Those are already wrong, okay? Now, one of these is correct. I have to have balance of charge. So on this side, I have a charge of 0, and this is 0 and a -1. So that side, oh, well, that does not appear correct. Well, let's check this one. This side has a 0, this is +1, and this is -1. That would equal 0, okay? Number 47, based on table J, which ionic equation represents a spontaneous reaction that can occur in a voltaic cell? So what I want you to notice is they all involve Fe and Mg, right? So let's get to table J. All right. On table J, let's find Fe, right, and Mg. Okay. So this indicates more active. In terms of metal, those are oxidized. Metals are good losers. And least active would be reduced, which is not what a metal prefers. Okay. So in this situation, in order for reaction to occur, magnesium would have to bump iron out of its space. So that means magnesium would have to start alone as a single element, and iron would have to start in a compound, and they would switch places. So if I look, which one do I need? I need magnesium starting as an element. Okay, so that means this is wrong and this is wrong because magnesium would be starting in the compound. And for number 2, they're both starting as metal. That's not a thing. It's got to be this one, number 4. Okay, 48. Given the equation representing a system at equilibrium, in this system, H2O liquid acts as what? Well, let's follow the H plus. So what happens here is the hydrogen goes this way because look on this side, the NH3 has one more hydrogen. So what is the water doing? The water is giving up. So it's donating. So already I know it's donating, so it's not accepting. And what is that a definition of? That is an acid. Okay. Number 49, which indicator is blue in a solution that has a pH value of 7.0? So this is a reference table question. So here we have the indicators. Which one is blue at 7.0? Okay, so at 7.0, that would be here. This one would be yellow. At 7.0, that's in between. We don't talk about it. At 7.0, that's over here. It's below 8. It would be colorless. 7.0 is in between these. Don't talk about it. 7.0 would be over here, be blue. And 7.0 would be here, so it would be yellow. Because remember, if it's below this first number, it's the first color. If it is above the second number, it's the second color. In between, it's a mixture of them, but I can't be specific in identifying the color. So the only one it looks like is what? Brom cresol green. All right, and the last one, which radioisotope requires long-term storage to prevent the risk of biological exposure? So let's go to a reference table. In this case, we're going to look at table N. And let's find each of these. We have N16 right here, K42, right? We have PU 239, and finally gold AU 198. All right, now let's look at the half-life. That one decays in days. This one decays in hours. This one decays in seconds. This one decays in, holy cannoli, a bunch of years. So which one is going to require long-term storage? This one, because it's going to keep decaying. Its half-life is so long, it's going to be releasing that radiation and decaying for a very long time. All right, now we are on to B2. Here is where the actual answer booklet comes into play. You can see there is, different amounts of space depending on what the question is, okay? And part B2 are the easier ones of the short answer questions. You can see it goes up to question 65, so the first 15 of the written questions. Okay, so I am going to skip the reading. I always just say go to the question and read the question. Sometimes you don't need to read anything else, and it will save you some time so you can go back and check your work. Okay. So state the number of valence electrons in an atom of sulfur 32 in the ground state. Well, the only thing that matters when I'm determining valence electrons is what element I'm talking about. So I go to the reference table, I go to the periodic table. Now, if you panic on the exam and you're like, I totally forgot what sulfur was. Okay, so then you start looking here, okay? But here is sulfur. Look at its atomic number. Okay, but here's where we want to find our answer in the electron configuration. The valence electrons is the last number. So my answer here is 6, right? So in my answer booklet, I would be writing 6. 52. State the number of neutrons in an atom of sulfur 33. So let's think about writing isotope notation like this. That 33 is the mass number, and it goes up here at the top. What number would go down here? Well, the atomic number, which we said is 16. So mass number is protons and neutrons. Atomic number is just protons. So what I would have to do is subtract those two numbers, and I would get 17. So my answer here, 17. Okay, now we're on to our next group. Again, I'm going to skip all this and just go directly to the question. Compare. Okay, I love this question. As soon as I see a compare, I love it. Either it is equal or one is greater. I mean, technically I could say one is less, right? But that's it. Those are the only options. I love it, okay? It's like giving you a whole hint of your answer. So compare the electrical conductivity of an alkali metal at STP with the electrical conductivity of a halogen at STP. So where are alkali metals? Right here in group 1, halogens over here in group 17. Okay, so the electrical conductivity, let's just make this wider so it's not doing weird things. Conductivity of an alkali metal, it's a metal, is greater, period, done. I don't even have to say anything else, okay? So this is exactly what I would put here, and I don't have to say more than that, okay? I could say if I want is greater than the electrical conductivity of a halogen. Okay, I could say that. What I don't want to say, this is a not, do not say it is greater. What the heck? Which one do you mean? Name the thing. So see how I said the electrical conductivity of an alkali metal? Bam, perfect. Now I know what I'm talking about. Okay. All right, and 55. Explain in terms of electrons. That means this word should be in my answer. Oh, wait, I skipped 54 first. Let's go back up here. State the type of chemical bonds formed when an alkali metal and a halogen react to form a compound. Let's look at my answer booklet. Look at this. See how I've got a short line? What kind of bonds between an alkali metal and a halogen? Ionic, right? Between a metal and a non-metal, right? So ionic. All right, now let's go back here where I started to jump ahead. Now number 55. Explain in terms of electrons why the halogens are all placed in the same group. So why are all of these halogens in the same group? Okay, so halogens are all in the same group because they have the same number of valence electrons. Okay, this gives them similar chemical properties. Okay, so I don't need to say that gives them similar chemical properties. This, though, is what I need to say, okay? I need to say that they're in the same group because they have the same number of valence electrons, Okay, that's what I need to say. Okay, or I could say the number. They all have 7 valence electrons. Okay, but I need to talk about the valence electrons. All right. Now we're done with 55. Now we're on to the next group. Again, skipping, just go to the question. All right, balance the equation. All right, so let's go to the answer booklet for this one because it's going to be a lot easier to balance it if I'm looking at the actual equation. Okay, so I'm going to do this, divide. I'm going to write, I have AG, what else do I have? S and AL, right? On this side, I have AG. I'm going to put it in the same order. And I'm going to look at how many I have right now. I have 2 of these, 1 and 1. On this side, I have 1, 3, and 2. Okay. So I'm going to pick something to try to balance. So, well, if I was balancing this first, right? This AG is by itself, so I'm not going to balance that one. This AL is by itself. So let's balance the S. So if I have 3 S's on this side, I need to have 3 S's on this side. But when I put that 3 as the coefficient, right, it also changes AG. Okay, so that is 6. Okay, so let's fix AL. This needs a 2, right? Times 2. So I have 2 total ALs. And then AG needs a 6, right? Times 1 equals 6. So now, if I check this, I should have 3 times 2 is 6 AGs. 6 times 1 is 6 AGs. 3 times 1 is 3 S's. This is a 1, or I can leave it blank, right? 1 times 3 is 3 S's. And then 2 times 1 is 2 ALs. 1 times 2 is 2. Beautiful. Love it. It's perfect. All right. Determine the gram formula mass of the aluminum sulfide product. Okay, so it's easy enough because literally there it is, right? Now notice I just have a line to write my answer, so I'm just going to use some of this space over here to do my calculations. My work is not required to be shown. Okay, now if you remember to find gram formula mass, you need to use the atomic mass or the gram formula mass for each of the elements and then multiply by the subscripts. So for sulfur, it's 32.065. Now I could use that number directly. I could use 32.065, or I could round it to 1 decimal point. And then for aluminum, it's 26.98154. I could use that number directly, or I am just going to use 27. Then I'm going to look at the subscripts. So for aluminum, I multiply by 2, right? And for sulfur, I multiply by 3, okay? So then what I'm going to do is add those together. So 54 plus 96.3 is 150.3, okay? And that is what goes on my line. So 150.3. Now, what's interesting to note is that the teacher guide here allows between 149.96 to 150.3. So that's it. It allows anywhere between, which 150.3 is there, right? If your answer is outside of this range, it is not accepted. So this is, so I get credit, okay? Number 58, show a numerical setup for calculating the number of moles of silver sulfide in a 546 gram sample of Ag2S, or silver sulfide. Okay, so first I need the formula. So go to the back of the reference table, and here's moles. Moles equals given mass over gram formula mass. So I'm going to write the formula. So moles, right, equals mass, or grams, over gram formula mass. So I'm trying to find moles, right? Now it gave me the gram formula mass right here, 248. So I put that for gram formula mass. And then it says there's this many grams. So that is literally what goes on the top, that 546. And that's it. It said show a numerical setup. Bam. Basically, pick the right formula and put the numbers in the correct spot. So I'm done. That's it. I finished question 58. Okay. And then we move on to the next section. Again, we're skipping the top and going right to the question. So question number 59, state evidence from the equation that the forward reaction is endothermic. What does endothermic mean? Endothermic means energy is absorbed. It's coming into the equation. Now, evidence from the equation. So what's the evidence from the equation that says that that reaction is endothermic? Well, this right here, okay? Energy, heat, is on the reactant side. So energy is on the reactant side. You could say heat is on the left side, okay? The kilojoules are on the reactant side. Okay, those are all possible answers. You just need one. Okay. Next, we have number 60, state in terms of reaction rate. So I got to talk about rate of the reaction, right? Why the concentration of HI remains constant when the system is at equilibrium. Well, that's because you have to remember something really important about at equilibrium, right? At equilibrium, right, in terms of reaction rate, the rates of the forward and reverse reactions are equal. You could just say the rates are equal, right? But I'm specifying the rates of the forward and reverse because I have to talk about rate. So at equilibrium, the rates are equal, okay? And then last for this one, question 61, state how an increase in temperature affects the concentration of HI. All right, so let me swap this color out. When I increase the temperature, right? How do I resolve that stress? So that is stressful for this poor equilibrium, right? How do I resolve that stress? Well, I need to get rid of some of that heat. I need to use it up. Well, here's where my equation is divided, right? There's where the arrows are. So everything else that's on the same side as what I'm trying to lessen is also going to go down. And what is on the opposite side will increase. So how will an increase in temperature affect the concentration of HI? The concentration of HI will increase. Now, why? I don't have to say the why, okay? But just to let you know, the reaction shifted to the product side or shifted to the right, okay, which is what caused the concentration of HI to increase. All right, we are on our last question set in part B2. Okay, so again, I tend to do this, just skip and start with the question. Sometimes I need this information up here and sometimes I don't. So let's just start. State in terms of carbon-carbon bonds why butane is saturated. So I need to go back to my reference table, okay? And where I need to go is table P and Q. So let's zoom this out a little bit. Okay, so table P tells me about carbon prefixes. But, so I've got 4 carbons. So 1, 2, 3, 4, connected in a chain. It was butane, right? So it ended with A-N-E like this one. So if I look at this model, that means it has all single bonds. So like this, right? So why is butane saturated? Because it is an alkane, right? And why is it an alkane? Because it has all single carbon-carbon bonds, okay? So it says in terms of carbon-carbon bonds, so I'm going to talk about that. So butane has all single carbon-carbon bonds. It does not have a double bond. It does not have a triple bond. You could say it has no multiple carbon-carbon bonds. Okay, that would also work. Okay. 63, identify the class of organic compounds to which the organic product in the equation belongs. Okay, now I need the equation. Here's the equation. Here is the arrow. So these are reactants and these are products. I need to find the organic product. That means it must contain the element carbon. So that's this. Okay. Now let's go to table R. Where in table R do we see something like this? Okay, why do I know I have to look here first of all? Well, I have more than just carbon and hydrogen. So table Q is not the answer. It's got to be in table R. Well, look, right here, I see this. The question is, what class of compound? So my answer is going to be halide. Okay, I could say halocarbon because that is an acceptable right here for class of compound, but that is straight up, that's my answer. Okay, 64. Based on the boiling point data, compare. Oh, love it. Here's another one. Compare. So that means, again, what does compare mean? Either the things they're talking about will be equal or one will be greater. Right? I mean, one will be less in reality, but really all I need to think about is there's basically two answers, okay? So let's go back. Based on the boiling point data, compare the strength of the intermolecular forces in 1-chlorobutane to the strength of the intermolecular forces in 2-chlorobutane. So before I even go to the information, I'm going to say the strength of the intermolecular forces. Now I need to figure out if it's equal or if one of them is greater. Okay, so let's look at the table. Well, all I have is boiling points. Now, are their boiling points the same? No, absolutely not. So that means the intermolecular forces are not the same. So equal is not a possibility. So one of them has to be greater. Okay. Which one will have greater intermolecular forces? The one where it has a higher boiling point, where it is harder for it to boil. It takes more energy added for it to boil. So the strength of the intermolecular forces is greater in 1-chlorobutane. Okay. And now for 65, so I just want to show you the answer booklet for 65. Okay. Is just a blank space. So that's either going to be a numerical setup, a calculation, or in this case, a drawing. Draw a structural formula for the 2-chlorobutane. Well, do you remember we looked it up? So but was 4. So I drew this for butane, right? So let's just transfer that over here. So butane 4, right? And it has these bonds, right? Which there will be hydrogens at the end, but I don't need to draw them. But now it says 2-chloro. So now go to table R, and you could see chloro is a Cl, 2 on the second carbon. So on carbon 2, 1, 2, put a Cl. Bam, finished, all set. Okay, I could draw it from the other end, but I don't need to. Okay, so that is the last question in part B2. We have one section left, and that is C. All right, so let me just show you one thing before we go on for question 65. So you can see this is what I wrote. What I want you to notice is at the end of each one of the lines that doesn't have a letter, that is implied to be a hydrogen. But here you can see you can count 2 from this side, or you can count from this way, right? Here's similar to what I drew, but on its side. But this is what I really want you to pay attention. This is from the answer guide. It says, do not allow credit if only some of the H atoms bonded to C are shown. So see here, no H's are shown. Here, all H's are shown. That's the only options you have. It's either all or none. Okay. Now we will go to part C. So these are the more involved written questions. So let's look at 66 through 68. Those are grouped together. So again, I am literally skipping all of this and going to the question first because maybe I need it and maybe I don't. State the number of significant figures in the mass of the hydrated CuSO4 sample used by student 1. Okay. Now, significant figures. So first I got to find mass of hydrated CuSO4. So it's this number right here, right? And I need the number of significant figures. So here's how you determine significant figures. You look at the number. Does it have a decimal point? Yes. Okay. When it has a decimal point, I start counting at this side of the number. And I look, is the first number a 0? No, that is not. So that is one significant figure. The next number counts. Every other number written counts. So how many significant figures do you have? 3. All right, 67. So if we look at the answer booklet for 67, you can see I just need to record the answer, so I don't have to show my work. I just need the final answer. Determine the percent composition by mass of water in the hydrated CuSO4 sample based on the data for student 1. So now I need the reference tables, and I need a chemical formula. I need a equation. And here it is right here. So the percent composition by mass, all right? So it's mass of part over mass of whole times 100. So I need mass of part over mass of the whole thing, okay, times 100. Now it says determine the percent composition by mass of water. So water is the part. So what is the mass of water? 1.02 divided by, what is the mass of the whole thing? Well, that was this, right? 3.00. Don't forget times 100. Okay, so I'm going to put that into my calculator. 1.02 divided by 3.00 times 100 is 34%. So my answer is 34%. Now, I could also write, based on significant figures, 34.0%. Those were the two answers that were allowed based on the answer key. Okay. Now number 68. So you can see 68 has a big space. So it says show a numerical setup for calculating the percent error for the percent composition by mass of water in the hydrated CuSO4 sample as determined by student 2. So now I need a chemical an equation again, and this time I need percent error. So percent error is measured value minus accepted value divided by accepted value times 100. So I'm going to do it kind of abbreviated by measured value minus accepted value divided by accepted value times 100. Okay, so if I go back and look, measured value minus accepted value divided by accepted times 100. Okay, so I have that. So now I need the measured value and I need the accepted value, right? But the percent composition by mass of water in the hydrated sample by student 2. Up here we did student 1. We didn't do student 2, right? So let's look. Student 2, now I'm going to read up here because I think I have something that will help. Student 2 determined the percent composition to be this. So that number is measured, so 37. And the accepted value is right here, 36.1. Okay. Oops, 0.1, 36.1, and this is 36.1. So I just have to plug the numbers in the right spot. So 37 minus 36.1 divided by 36.1 times 100. And that's it. I don't solve it. I just do that. Okay? All right, questions 69 through 71. Skip, go to the question. Again, maybe I'll need it, maybe I won't. Let's find out. State the number of electrons shared between the nitrogen atom and one of the hydrogen atoms in an ammonia molecule. Well, this is ammonia, right? So what does ammonia look like? Well, let's go to the reference table. And nitrogen has how many valence electrons? 5. Hydrogen has how many? 1. So nitrogen has 1, 2, 3, 4, 5 valence electrons, and hydrogen has 1. But I have 3 hydrogens, right? So I will end up with this. 1 hydrogen there, 1 hydrogen there, and so on. Okay? Now, how many electrons are shared between the nitrogen and one of the hydrogens? It's 2. It's 1 bond, right? That's it. Number 70, identify. So this is, I'm just naming the noble gas that has atoms in the ground state with the same electron configuration as the nitrogen atom in a molecule of ammonia. Okay, well, let's go to the reference tables. Here is nitrogen, right? So let's look at our model. How many valence electrons does nitrogen have around it here? 1, 2, 3, 4, 5, 6, 7, 8. Okay, which noble gas? Right here. Okay, because nitrogen had 7 valence electrons, but it's sharing 3, so it has this configuration. So it will be neon. And then determine the energy required to break all of the bonds in 0.250 moles of HH bonds in the H2. Okay, well, let's look. It says the bond energy of an HH bond is this, 436 kilojoules per mole. I have this many moles. So how do I find out how many kilojoules? I do, let's look at the calculator. I would do 0.250, that's the number of moles, times 436 kilojoules per mole. So that means it is 109 kilojoules. Less than a mole because I literally have less than a mole, right? That should be logical, okay? So if I look at the answer key for this one, I'm just writing a short answer for 71 right here on this line. Okay, number 72 and 73 are together. I mean, I'm probably going to need this, but let's just go to the questions. Compare. Ooh, what did I tell you about compare? It's either going to be equal or one of them is greater, right? Those are the only options. So compare the density of the helium in the cylinder when the volume is 50 milliliters to the density of the helium in the cylinder when the volume is decreased to 25.0 milliliters. Okay, so think about it. Here is in a 50 milliliter container, right? Here is a 25 milliliter container. I have the same number of particles. So let's just say 1, 2, 4, 7, 8, 9, 10. Let's say I have 10 particles. Okay. Density is how tightly packed those particles are. So will the density be the same? No. Where will it be greater? Right here. So the density in the 25 milliliter container will be greater, okay? Will be more, okay? You could also say the density in the 50 milliliter container is less, okay? And then state one change in temperature and one change in pressure that will cause the gas in the cylinder to behave more like an ideal gas. Okay, so here's the thing about ideal gases. They love tropical vacations, right? So what does that mean? That means raise the temperature. That's one way to make a gas more ideal, make it be on a tropical vacation. So raise the temperature or lower the pressure. So I think about stress, right? So I need to raise the temperature and lower the pressure. So if you look at the answer booklet, right here you have to say what you do to temperature and what you do to pressure. So we're going to raise, but don't just draw an arrow, right? Raise the temperature or increase the temperature, and lower the pressure or decrease the pressure. Okay. All right, 74 through 76. Okay, I got a lot of information. I'm probably going to need it, but let's go to the first question. Determine the number of moles of NaNO3 in 0.15 liters of the solution. So here is the solution, here is the moles. So 0.15, okay, go up until you hit the line, go across and read that number. So you can see for question 74, it's just a simple answer like this. So looking at that, what would you say? I would say maybe we're at 0.12 moles. And in fact, the answer key is going to allow any answer between 0.11 to 0.13. So 0.11, 0.12, 0.13. Okay, that is acceptable. Number 75, write a chemical name for NaNO3. Well, since it's more than 2 elements and I don't have carbon involved, I need a reference table, and that is table E. So what do you see on table E that is in that formula? Well, we have this. So the name of the NO3 part is nitrate. What is the name of the other part? Well, if you don't know the name of that one, right, on the periodic table, it's right here. But if you don't know the name of it, you just go here and you could see that it is this. And we don't change the ending. We only do that for the last one when it's a single element. So the name of this is simply sodium nitrate. And then 76, compare the boiling point of the solution in sample 1 at standard pressure to the boiling point of water at standard pressure. Again, we have a compare, right? So it's either equal or one is greater. So here is the boiling point of water, right, at 100 degrees Celsius. When you add something to the water, the boiling point goes up. The freezing point of water is 0. And when you add something to water, the freezing point goes down. So the boiling point of water is less than the boiling point of the solution. Or we could say the solution has a higher boiling point. Okay, we could just say water has the lower boiling point. Lots of ways to say it. Whether you say higher or lower depends which one you're talking about. So water has the lower, the solution has the higher. Okay. All right, now we are on questions 77 through 79. Okay, first what I want to point out is this says electrolytic. How do I know it's electrolytic? Look at this, it's got a battery, okay? Now it says one of the electrodes are made of copper, Cu. The other one is a bracelet, but it doesn't tell us what metal, it just says a different metal, okay? Now what you need to know about electroplating, okay, is that this copper is going to coat the bracelet, okay? So that means that the copper piece will get smaller, right? And the bracelet piece will get larger, right? So some of the copper will enter the solution, right? And then what will happen is the copper will coat the bracelet, okay? All right, so if this piece is getting smaller, that means it must be losing electrons, right? If it is losing electrons, that is LEO, right? That is oxidation, okay? All right, which means this must be the opposite, okay? So it says, for the first question, identify the electrode that attracts the Cu2+ ions as the cell operates. Well, which way did I say they were moving? To the bracelet. Okay, so the bracelet is doing the attracting. You can also see up here that the bracelet is connected here to the negative electrode. So you could say to the negative electrode. Okay, now you could also say, because this is an electrolytic cell and the negative one is the cathode, okay, so that is the cathode, all right, so the bracelet, the negative electrode, the cathode, those are all acceptable. Now determine the oxidation state of sulfur in CuSO4 2 negative. Now, this has a lot of different parts to it, so I'm going to encourage you to look right here at table E. When you look at table E, you will see that SO4 has a 2 negative charge, right? So SO4 is 2 negative, okay? Now, in order to find the oxidation state of sulfur, right, I need the oxidation state of oxygen. Well, that I can get from the periodic table, -2, okay? So that means with 1 sulfur and 4 oxygens, and oxygens are -2, it will equal -2, right? It's going to equal that number. 4 times -2 is -8, right? Equals -2. Add 6 to both sides. Add 8 to both sides. I was already jumping ahead to the answer. Add 8 to both sides, and I get +6 as my answer, okay? So +6 or 6 positive are correct, all right? Now, write a balanced half reaction equation for the reduction of Cu2+ ions that occurs in this cell. So reduction, it means it gains electrons. So how many? I don't know, but it's going to be gaining electrons. When it gains electrons, it's going to end up as the atom. That's how it coats it. So when it goes from 2+ to just copper, that's 2 electrons. Because remember, if we draw this number line quickly, 0, 1, 2, -1, moving this way is LEO, losing electrons. Moving this way is GER, gaining electrons. It also points to the side of the equation that you need the electrons on. So see right here, okay? Also, I need conservation of charge. So this is +2, this is -2, this is 0. But +2 and -2 does equal 0. So wham, the charges balance, okay? All right, now as a fun fact, just as a note, see how I wrote electron like this with the negative sign? If you write this, bam, you cannot get credit. You must write E with the negative, okay? All right, 81 through 82 are together. Now it says complete the equation in your answer booklet. Okay, so let's look at our answer booklet. Here we go. What do we see here? HCl and KOH. So let's go to a reference table. Here's HCl, it's a Here's KOH, it's a So here's what you have to remember, right? Acid plus base yields what? Water plus salt, right? Water's formula is H2O. How else could you write it? HOH. That's acceptable. Okay. Now I need to figure out what the salt is. Well, the OH was used to make water. The H was used to make water, right? H is +1. OH is -1, which means K is +1, and Cl is -1. So it is going to be K because it was written first, Cl because it was written first. I mean, I don't know, that one came out weird when I wrote it. That Cl should not be little. So KCl. This is what goes here, and H2O or HOH for that blank. Why? Because acid plus base yields water and salt. Okay. Number 81. State the pH value of the solution when the H+ ion concentration in the acid has decreased by a factor of 10 compared to its original value. So first let's find the pH of the acid. It's 1.1. Okay, so it starts at 1.1. Now the H+ ion concentration decreases. Okay, so here's what you have to remember about pH. From 0 to 14, the most H pluses are over here. The most OH negatives are over here. So if the H pluses are decreasing, pH is moving this way, right? Now it decreases by a factor of 10. And on the pH scale, because it's based on logarithms, okay, the pH goes up by one number because it's based on 10. So a factor of 10 means it goes up one number, so it would be 2.1. Okay. And then number 82, determine the molarity of the HCl aqueous by using the titration data. Okay. So that means I need a formula, right? So it is for titration right here. Okay, so what I typically do, so let's go to our answer booklet, which you can see all I need to do is write the answer. It doesn't really give me space to work it. So let's use this space down here. Okay, MAVA equals MB VB. Make my list of variables, MAVA MB VB. Okay, now go back to the question. 15 milliliters of this, so that's VA. Right. Then we have 8 milliliters of 0.15 KOH. So 8 milliliters, 0.15. Okay, I'm going to check one thing. What acid do I have? HCl. Well, there's one H, and KOH has one OH. Why does that matter? Because notice that the MA is the molarity of the H+, and the MB is the molarity of the OH. So sometimes I have to multiply by 2 or 3 if there are more of them. But in this case, I don't. Okay. So now I just substitute. So MA is X, VA is 15. So 15X equals 0.15 times 8. So let's do 0.15 times 8 is 1.2. So 15x equals 1.2. Divide by 15. Okay, 1.2 divided by 15 equals 0.08. 0.08 molar is the answer. Okay, and that was 82. Okay, and then we have our last ones. 83. Based on table N, states the decay mode for uranium-235. So I need obviously table N. Okay, uranium-235 down here. Here is the decay mode. So what can I write? Well, that's this, right? So I can write alpha particle, I can write this, I can write this, I can write this. Okay, so I am going to choose to write alpha particle, or just alpha. Okay, complete the nuclear equation in your answer booklet. So let's go to the answer booklet. Okay, let's look. Remember, this is the divider between the two sides. So on both sides, it has to be equal. If it's 141 on this side, I have 0 so far. That means I need 141 on this side. On this side, I have 56 total. On this side, I have -1. So that has to be 57. Why? Because 56 equals -1 plus x. So I add 1 to both sides. Okay. But now I need a symbol for that element, right? So I'm going to look at the periodic table, and I need to find atomic number 57, and there it is, okay, La. So those are all the parts I need, okay? And now the last question, compare. Okay, remember, equal or 1 is greater. Compare the amount of energy released by the fission of 1 mole of uranium-235 to the amount of energy released by the combustion of 1 mole of octane fuel. The amount of energy released from fission is much greater. I could just say greater. There's more energy from the fission reaction, lots more. Remember, a small amount of mass is converted to energy, which makes any kind of nuclear reaction have way more energy released. You could say the combustion reaction has less. The nuclear reaction has more, way, way, way more. And there you go. That is the entirety of the August 2023 exam. We made it.